Let's walk through the Group Relative Policy Optimization (GRPO) architecture, which is a reinforcement learning algorithm specifically designed to optimize large language models for complex tasks like mathematical reasoning and coding. GRPO is designed to be more efficient and memory-friendly than traditional methods, such as proximal policy optimization (PPO). Let's explore it in 4 parts. The Group Relative Policy Optimization architecture. The main advantages of using GRPO for large language models. How does GRPO improve the reasoning capabilities of LLMs? How does GRPO's group-based advantage estimation work? Now let's explore how GRPO architecture achieves this. The first. Key components of GRPO. 1. Policy model. In GRPO, we use a single policy model, which means there's no need for a separate value function, unlike PPO that typically uses a second large neural network for value estimation. This simplification reduces both memory and computational requirements. 2. Group-based advantage estimation. Instead of relying on individual response evaluations, GRPO generates multiple responses per prompt. The mean reward of these responses is used as a baseline to calculate the advantage. This helps reduce the variance in advantage estimates, making the process more stable. 3. Reward model. GRPO uses a reward model to evaluate each response. This model is trained on datasets that compare different outputs for the same prompt. Since GRPO's approach is comparative, the reward model aligns perfectly with this structure. 4. KL divergence constraint. GRPO ensures stability in the learning process by adding a KL divergence term to its loss function. This term ensures that the policy updates don't deviate too far from the reference policy, maintaining stability in the learning process. The second, mathematical formulation. Let's break down the loss function, which is a combination of 2 key components. 1. Advantage maximization. This term helps the model focus on actions that lead to better rewards. Mathematically, it is represented as follows, where AJK equals RJK minus RJ, with RJK being the reward for the K response and RJ the average reward for the prompt J. 2. KL divergence penalty. This component helps control the distance between the current policy and the previous policy to ensure stable updates. It is represented as follows. The total loss function is then the sum of these 2 components. The third. Advantages of GRPO. 1. Memory efficiency. By removing the need for a value function, GRPO reduces memory usage by 40 to 60% compared to PPO. 2. Stability. The inclusion of KL divergence ensures that policy updates remain stable and avoid large erratic changes. 3. Efficiency. GRPO allows for training models at a significantly lower cost than traditional reinforcement learning methods. The fourth, challenges and considerations. 1. Variance in group rewards. If the group size is small, the mean reward estimates can have higher variance, which might affect stability. 2. Dependence on reward model quality. The performance of GRPO is heavily influenced by the quality of the reward model used to score the responses. A poor reward model can degrade the effectiveness of the algorithm. In summary, GRPO optimizes large language models efficiently by leveraging group-based advantage estimation and eliminating the need for a value function, making it an excellent choice for complex reasoning tasks, especially when working with limited hardware resources. Now let's go over the main advantages of using Group Relative Policy Optimization, GRPO, for large language models, particularly for tasks that require complex reasoning, such as mathematics and coding. The first, memory efficiency. Reduced memory usage. One of the biggest benefits of GRPO is that it eliminates the need for a separate value function, something typically required in algorithms like PPO. This value function is usually another large neural network that consumes a lot of memory. By removing it, GRPO significantly lowers memory requirements, which is especially helpful when training large models on hardware with limited resources. The second, simplified advantage estimation, efficient advantage calculation. In GRPO, The model generates multiple responses for each prompt, and then uses the mean reward of these responses as a baseline for calculating the advantage. This method simplifies the calculation process and helps reduce variance in advantage estimates, leading to more stable training. It's an improvement over traditional methods that can sometimes struggle with noisy or highly variable estimates. The third, stable training, KL divergence constraint. GRPO includes a KL divergence term in its objective function. This term helps ensure that the updates to the model's policy don't deviate too far from the original reference policy. By controlling these deviations, GRPO helps maintain stability during training, preventing large and erratic shifts in the model's behavior. The fourth, improve performance on complex tasks, enhanced reasoning capabilities. GRPO has been shown to improve model performance on tasks that require complex reasoning, such as solving mathematical problems or understanding code. For example, models like DeepSeek R1 have achieved significant improvements on benchmarks like math when trained using GRPO. This demonstrates that GRPO can help language models handle more intricate and demanding tasks effectively. The fifth, cost-effectiveness and scalability. Reduced computational costs. Since GRPO doesn't need a separate value function, it helps reduce computational costs associated with training large models. This makes it more scalable. You can apply it to larger models or run it on systems with fewer resources, making it ideal for large-scale applications where computational efficiency is crucial. The sixth, robust and self-corrective reasoning, qualitative improvements. One of the more fascinating outcomes of using GRPO is that it encourages robust and self-corrective reasoning. For instance, in tasks like visual maze navigation, models trained with GRPO have shown the ability to improve their reasoning over time, adapting and correcting mistakes. This suggests that GRPO fosters deeper reasoning capabilities that go beyond simple fine-tuning. In summary, GRPO offers a powerful and efficient method for fine-tuning large language models. It's especially useful when you need complex reasoning and are working with resource-constrained hardware. With its ability to improve memory efficiency, simplify advantage estimation, ensure stable training, and enhance performance on difficult tasks, GRPO is a valuable tool for advancing the capabilities of large language models. Now let's break down how Group Relative Policy Optimization, GRPO, helps improve the reasoning capabilities of large language models. GRPO takes a reinforcement learning approach that is both innovative and efficient, and here's how it works. The first, efficient advantage estimation. 1. Group-based approach. One key feature of GRPO is its group-based approach. Instead of relying on a single response, GRPO generates multiple responses for each prompt. It then uses the mean reward of these responses as a baseline for calculating advantages. This method simplifies the advantage calculation process and reduces variance in the estimates, making the training more stable and efficient. Compared to traditional methods like PPO, this is much more streamlined. 2. Reduced memory usage. GRPO also eliminates the need for a separate value function, which is typically another large neural network. This means GRPO can reduce memory requirements, making it much more suitable for resource-constrained hardware like GPUs with limited memory. The second, improved performance on complex tasks. 1. Mathematical and coding reasoning. GRPO has been shown to significantly improve performance on tasks that require mathematical and coding reasoning. A good example is the DeepSeek R1 model, where GRPO helped boost performance on complex benchmarks like math, problems that require deeper logical and numerical understanding. 2. Visual spatial reasoning. But it's not just about numbers. GRPO also improves visual spatial reasoning, which is crucial for tasks like maze navigation. In these tasks, GRPO encourages the model to develop more robust and self-corrective reasoning. This means the model can correct itself if it takes a wrong turn, so to speak, during the reasoning process. The third, emergent chain-of-thought reasoning, self-corrective behavior. One of the most interesting aspects of GRPO is its ability to encourage emergent chain-of-thought reasoning. This means that the model doesn't just spit out an answer, it thinks through the problem in a series of steps. And if it makes a mistake, it can self-correct. We see this in models like DeepSeek R1, where GRPO promotes aha moments, moments when the model reevaluates previous steps and corrects its reasoning. This kind of behavior mimics how humans think critically and self-correct. The fourth, multi-stage training pipelines. Combination with supervised fine-tuning, SFT. GRPO is often part of a multi-stage training pipeline. This means that GRPO's initial reinforcement learning training is followed by supervised fine-tuning. While GRPO helps the model improve reasoning, SFT can further refine the model's language coherence and readability. The combination of both techniques helps produce models that can reason well and communicate their thoughts clearly. The fifth, cost-effective training, reduced computational requirements. One of the biggest benefits of GRPO is that it reduces the computational cost compared to traditional RL methods like PPO. This means you can train large models without needing huge computational resources, making it cost-effective and feasible to train powerful models even on more limited hardware. In summary, GRPO is a powerful tool for enhancing the reasoning capabilities of large language models. Its efficient advantage estimation, emergent reasoning behaviors, and cost-effective training make it an ideal choice for complex tasks, from mathematics and coding to visual spatial reasoning. By fostering self-corrective behaviors and working well with other training techniques like supervised fine-tuning, GRPO helps models think critically, improve their accuracy, and adapt to new challenges. Now let's break down how Group Relative Policy Optimization, GRPO, uses group-based advantage estimation to improve the training process, especially when it comes to large language models. This method is central to GRPO's efficiency and effectiveness. The first, key steps in group-based advantage estimation. 1. Response generation. For every prompt, GRPO generates a group of multiple responses. Typically, this could mean generating around 64 samples per question using the current policy model. This group of responses allows the model to explore different possible answers to a prompt. 2. Reward calculation. Each of these responses is then scored using a reward model. This model evaluates how well the response performs based on various criteria, such as accuracy and coherence. Essentially, it's assessing how good each response is. 3. Mean reward calculation. After scoring all the responses, GRPO calculates the mean reward of all the responses for a given prompt. This mean reward acts as the baseline when estimating advantages. The idea here is to compare individual responses against the group's performance. 4. Advantage estimation. For each response, advantage is determined by subtracting the mean reward from the reward of that individual response. To further stabilize the learning, this advantage is often normalized by dividing it by the standard deviation of the group's rewards. This helps in reducing variance in the advantage estimates, leading to more stable training. Mathematically, the advantage for a response can be written as follows. Here, Ri is the reward for response I, and mean and stead are the mean and standard deviation of the rewards within the response group. The second, benefits of group-based advantage estimation. 1. Memory efficiency. One major advantage is that GRPO eliminates the need for a separate value function. In other methods like PPO, a separate neural network is often required to compute the value function, which consumes a lot of memory. With GRPO, this is not necessary, which reduces memory usage significantly. 2. Reduced variance. By using the group's mean reward as a baseline, GRPO helps to reduce variance in the advantage estimates. This results in more stable training, which is important for improving the overall performance of the model. 3. Alignment with reward models. The group-based method fits well with reward models, which are often trained on datasets that compare different outputs for the same prompt. This makes the approach more aligned with how reward models are typically designed and helps maintain consistency in the learning process. The third, mathematical formulation. The policy update in GRPO is driven by a loss function that takes the advantages calculated from the group-based approach into account. The loss function looks like this. In this equation, AJK represents the advantage for response K in prompt J. Beta is a parameter that controls the KL divergence penalty. This penalty ensures that updates to the policy are stable by limiting how much the new policy can differ from the old policy. In summary, GRPO's group-based advantage estimation is an efficient method that simplifies the calculation of advantages, reduces memory usage, and aligns well with reward models. These characteristics make it an excellent approach for training large language models as it results in more stable, efficient, and cost-effective training.